Okay, fine. See, when you look at maybe the gas turbines, the axial flow compressor is one particular component, which may call it as maybe something like an heart of that particular whole gas turbine engine. And the main reason we go for this kind of axial flow compressor is whenever we try to involve large pressure ratios. One is the large pressure ratio, and second one is when we are trying to handle huge mass flow rates. Huge mass flow rates and large pressure ratio, if you are looking at, we try to look into this axial flow compressors. Okay, that's one of the major reasons. Now, see axial flow compressors, that syllabus there. Okay, so axial flow compressors are used. Okay, axial flow compressors are used when we are dealing with large volumes of air and high mass flow rate. Okay. At the same time, uh, large volumes of air are nice, both are same, and also uh, high pressure ratio. Large volumes of air and high pressure ratio. Okay. And the advantage of going for this axial flow compressor is I can do so stage compression. The stage compression is better. That means if I want to get a pressure ratio of 30, say if I want to get a pressure ratio, so PR of 30, I can go for maybe 5 stages or 4 stages where each pressure ratio may be in and around 3 or 4. Okay, so first stage I'll increase from for maybe atmospheric pressure to 3 bar or 4 bar, then I'll go to 8 bar, then I can go to 16 bar like that. So in stage wise I can do the pressure, maybe the pressure increase I can do it. That's one particular thing. And also, if you have some kind of an restriction on the size, the diameter, okay, if you have a fixed maybe a diameter size for a given diameter size, for a given diameter size, okay, say for example I want to have my compressor for around 600 mm or 800 mm, something I'm going to do. So if that is the case, actually we will prefer axial flow compressors. Okay, so the advantage what I told, large volumes of air. And if when you look at the pressure ratio, so this pressure ratio, it has been found experimentally that whenever I have a pressure ratio more than 30, more than 30, maybe I want to get a pressure ratio of 40, 45, 50, it's very difficult to obtain in case of a maybe a centrifugal compressor. Okay. And also, if you look at the gas turbines, see, if you look at the gas turbine engines, their thrust developed per frontal area, we call it as thrust developed per frontal area. Frontal area means the area of that particular turbine which comes in contact with your maybe what with the air, or maybe to be very precise, it can be cross sectional area. If this particular thing thrust develop a frontal area, I want to get more, then we'll go for axial flow compressors. These are one of the major reasons why we prefer to go for a maybe axial flow compressor. Now, when we will go for a centrifugal compressor, so centrifugal compressor is maybe we can tell that it is slightly when I'm not interested in going for large mass flow rates. Okay, so when I'm looking at only the pressures. So when I'm looking at only the pressures actually. This is about your axial flow compressor. Now, when you come to centrifugal compressors, centrifugal compressors, okay, are used under different situations. Okay, maybe depending upon the pressure ratio, I can classify as fans, blowers, and at the last it will be compressors. Okay, and they're all, I think, incompressible fluids. So either the axial flow compressor or incompressible, maybe your this thing. So we go with maybe compressible fluid, air, or you can go with incompressible fluid. If incompressible fluid, if you use actually maybe water or air, it becomes a centrifugal pump. That's it. Now, if I take the fan actually, if I take the centrifugal compressor, one modification fan, so here the pressure ratio is very, very small. So if the pressure ratio is in the range of around 1.02 to 1.07, okay, 1.02 to 1.07, I call, so even though the centrifugal action, see the compression is there because of the centrifugal action, very low pressure and quantity of the air, see, the quantity of it can't handle large volumes of air. So when I want large volumes of air, I'll go with the axial flow compressors. So if I go for the centrifugal compressor, the quantity of the air is less. At the same time, size also matters. Now, if I go to fan blower, which is a bigger version of a centrifugal, maybe a fan, which is slightly bigger than, or maybe in terms of pressure ratio, I'm telling. Blower, the pressure ratio will be slightly, maybe I can call around 1.1 and up to 2. Maybe inlet is 1 bar, outlet is 2 bar, 1.8 or 2 bar and all. If that is the case, I call that as a blower. It is not very high pressure, but see, comparatively here, it can handle more mass. Your fan won't handle that much of mass of fluid, but slight increase in the pressure. And the blower will be able to handle slightly a mass greater than your fan at a higher pressure ratio. So you want it to be little bit high, more mass, not comparatively maybe axial flow compressor, it is much less. But compared to your fans and blowers, I'll be able to handle little bit slightly more mass and pressure ratio more than 2. Okay. If I go for, we call it as a centrifugal compressor. So with a pressure ratio more than 2, I will go with the compressor. So here also I can go for single stage and multi-stage. But single stage has limitation with respect to pressure ratio. Even multi-stage also, centrifugal compressor, I can't go for just like the axial flow compressor where I can go up to 16 stages or 17 stages, 19 stages and all we can do in a axial flow compressor because maybe the diameter is almost remain the same. But the centrifugal compressor, the problem is with the space. So I can go for either 2 stage or 3 stage. Okay. Now, if it is a single stage compressor, so my pressure ratio will be between 2 to maybe 8 or 10. Okay, 2 to 8 or 10, somewhere around that actually. If I go for a multi-staging, if I go for a multi-staging, my pressure ratio will be around 10 to 18 or something, so 10 to 20 you can put. So if you go for a higher pressure ratio, the usually preferable is axial flow compressors. Okay. Now centrifugal compressor is also called as radial flow compressor. The centrifugal compressor is also called as radial flow compressor. Why it is? Because the flow is in the radial direction. The flow is in the radial direction. So centrifugal compressor is also called as a radial flow compressor because the flow is in the radial direction. Radial direction. And as I told it, maybe handles less amount of mass flow rate and maybe pressure ratio in and around 15 or 20, whatever it may be, to the max. That's it. So this is about a simple description of your axial flow compressor and your centrifugal compressor. This is for axial flow compressor and centrifugal compressors. Maybe description wise. So if you look at the axial flow compressor, usually we have classification. You have usually a drum type and a disc type. Okay, so drum type, one particular thing, it is preferred whenever I try to have a single rotor. That means the rotor diameter remains constant. On that, maybe your compressor casing will be like casing will be tapered. But if I go for a disc type, actually, your rotor will be tapered. So if you want, I can show the diagram. So if I look at the axial flow compressor, the axial compressor. So we have one is either drum type or the second one is disc type. Okay, what is the drum type one? So a drum type one will be something like this, where your casing will be tapering. Your casing will be tapering in this direction, and your shaft. So this is my axis, and I do have a shaft on this. So this is just to ensure that I have a smooth entry of the fluid. That's it. Okay. So this is my rotor. Okay. This is your rotor. On the rotor, I'll be having the blades. So these are called as rotor blades. These are called as, maybe I can start with a bigger blade, then I can go on decreasing the blade size. Okay. This is on the rotor. These are my rotor blades. Okay. Then I'll be having the stator blades like this, which are coming in between your. This is your. Just I'm showing. So they're all aerofoil shape. Just I'm trying to show the cross section kind of things. So this is where your air intake will. This is your air intake. Air enters and the compressed air will be coming out here. If you look at it, what will happen? The drum is tapered. This is a drum type. Okay. This is a drum type. Okay, rotor. It's a drum type rotor because the rotor resembles a drum. Okay. Now the disc type, what will happen? If it's a disc type rotor, what will happen? So let me write that sketch. Okay. Then your rotor will be in the form of a disc actually. So what they do is actually, so this is your inlet, and so this will be tapered like this. Okay, and there will be discs actually. So in between, they are arranged in the form of a discs. Okay, these are the discs actually. The discs are arranged in different diameters, and they will form. These are your discs actually. They are arranged, and I'm going to get a disc type. So on this, I'll be having the blades like this. On this, I will be having the blades. These are my rotor blades. So I'll be having the rotor blades, and then I'll be having a constant. Your stator is almost flat. Okay, your stator is almost flat. Okay. On the stator, I can have the blades like this in between. So this is how it is. So what I am showing is just a rough sketch of it, and air will be entering here. This is your air inlet. This is this type axial flow compressor. They are all axial flow compressors. Stator, this is the arrangement. Okay. Now, one important thing what we have to, maybe if you go for a centrifugal compressor, the whole arrangement will be maybe something like I do have a rotor like this. Okay, the whole centrifugal compressor will be something like this. Okay, this is about axial flow compressor, and for a centrifugal compressor, it will be something like this, where I'll be having a drum like this. Okay, this is my drum. So on the drum, I'll be having your fins or vanes. Okay, these are my vanes. So this is your shaft, and the shaft will be rotating. So this direction, whatever it may be. And if you look it from the side, actually, so this will be your rotor. Okay, on the rotor, I'll be having a blade like this. Okay, this will be your blade from the side. So now, why it is called a radial flow compressor? Because so this is your, see, this is where I have my axis. See, this is where your axis, the shaft is here. Okay, the shaft is here. So this is the shaft actually. The flow is in the radial direction. The flow is in the radial direction, and here the flow is in the axial direction. That's why it is based on the flow. This thing I can classify this. Maybe see if you look at it, it may be having, see, just what I'm trying to show is just a rough sketch. So there may be a guide vanes. So there may be a guide vanes just at the exit to this. So what is the purpose of the guide vanes or your casing in case of a compressor is to convert the kinetic energy to static energy or the static pressures. So the flow will, maybe the fluid will enter at the center, then it gets compressed. Its kinetic energy increases in the rotor. Then whatever the increase in the kinetic energy, that gets converted to corresponding pressure in the guide vanes or in the casing, and then we'll have the output. Okay, that's how the maybe you, whether you take for a fan which is closed or a blower or the compressor, same thing. Only thing is depending upon the pressure structure. Okay. Now, when you look into this kind of maybe a centrifugal or the axial flow compressor, so usually we try to arrange it in different way. I was telling you that you have arrangement of this particular thing. One is multi-staging. So what is this multi-staging? So I have series multi-staging. Series multi-staging. So arrangement of these compressors in series. What it is actually, say I have one first stage compressor. Suppose this is my first stage compressor. I have, okay, it has an inlet. Okay, it enters at maybe some atmospheric pressure. Let me call it as P1. Okay. Now the output, it goes with a pressure output P2. So what will happen, and the output with a discharge Q. See Q with a discharge Q and the output P2. So what I'm going to do actually, I will take the output from this particular compressor and give it as an input to the second stage of the compressor. I'm going to give it to the as an input to the second stage of the compressor. So this is my second stage. So the pressure will be here, it is P2. It comes out with the pressure P2 and it enters P2 to the next stage. Then it goes out with a higher pressure P3, but mass flow rate remains the same. The mass flow rate remains the same. I can go to the third stage. So this may go to the third stage. This can go to the third stage. Same thing follows. So it goes to the third stage. This will be P3, and I have the third stage compressor. The third stage compressor. This is my third stage, and it comes out at P4 with same discharge. That means Q. So when this series arrangement is considered, whether it is a maybe you have your centrifugal compressor, how this particular thing is done. So whenever I want to get same discharge and high pressures. I speak of centrifugal, but in axial you don't have this thing because the blades are arranged. See, if you go to the axial flow compressor, see this is forms your first stage. This forms your second stage. This forms your third stage. That is one stator, one rotor, one stator, one rotor, one stator, one rotor forms one stage there. So they're arranged one after the other. I don't have this arrangement and all. So what is the thing I'm going to get actually? It is I'm going to increase the pressure, everything. At the same time, see the mass flow rate which enters, there also the same mass flow rate. Because the mass flow rate entered the first stage will be very high. But in case of a centrifugal compressor, if I go for parallel multi-staging, I can do something. I will get more mass flow rate. So it depends on the application. So if I go for parallel multi-staging, if I go for parallel multi-staging, what it is. So what I will do actually here, I have all my compressors like this. Okay, this is my first stage compressor, second stage compressor, and third stage compressor. Okay, all the compressors are drawing the air from same this thing. So that is atmospheric, we call it as P1 or PA, whatever it may be. So then they're all compressing to the same pressure. Let me call it as P2. But here, if I call it as Q1, if I call this as Q2, if I allow this, maybe Q1, Q2, Q3 may be the same. But I am going to connect it to one particular manifold. That means what will happen here? See, Q1 plus Q2 plus Q3. If Q1 and Q2 both are same, it will be the 3 times the discharge. Okay, 3 times the discharge. If, okay, Q1 and Q2, Q3 are same, then I'm going to get 3 times the discharge. So here, when I will go actually, if the same exit pressure and I want higher discharge. If I want higher discharge, I will go and I will go with the parallel multi-stage. So series arrangement and parallel arrangement. These are the two arrangements what we come across in case of what we call it as maybe centrifugal compressors. So any doubts here?
No, sir.
Yes, you can unmute and speak. Any doubts with respect to simple operation, elementary operation of the axial flow compressor or a centrifugal compressor?
No, sir. It's clear, sir.
No. Okay, fine. If that okay, then we'll move to the operations. Now, see, whenever we come across this particular thing, there is some amount of work done actually. There is some amount of work done. And we all deal with what is called as a pressure ratios. We all deal with what is called as a pressure ratio. And it has to work under that particular pressure ratio. So pressure ratio is one particular thing which has to be we're looking at actually. So if I try to look at the pressure ratio, what comes into our mind actually? The most important thing that comes to our mind is actually the steady flow energy equation, which you might have studied in your maybe thermodynamics course. So let us try to obtain the expression for the pressure ratio. Obtain the expression for the pressure ratio, okay, of a compressor. It can, I'm not telling that it is centrifugal or it is axial, because it is common for both centrifugal and axial. Okay. Now let us take a single stage compression and the HS diagram corresponding to that. Suppose this is my enthalpy and entropy HS diagram, and I do have the pressures going in this direction. Okay. Now how the compression will take place? If suppose this is my P1, this is my P1, this is my P2. Okay, the compression will be from point 1. If it is isentropic, it will be point 1 to point 2. And if it is an actual one, so it will be, because entropy has to increase. So this is the path what I'm going to follow. So if it is, if I go with maybe what we call it as maybe stagnation, then this will become P01 and P02. So I can go with that also, doesn't matter. So P01 and P02. So this will be 0, 1, this will be 0, 2 dash, this will be 0, 2. So this is an isentropic, and the one in the brown is the actual, and this is ideal or isentropic. Okay. Now let us write the steady flow energy equation. Steady flow energy equation. If you look at it actually, so what we have is actually the discharge at the mass flow rate, then your m dot will be equal to your h1 plus v1 square by 2 plus g into z1. I can write, instead of h, I can write, see, h is nothing but u plus pv, where we have the internal energy plus pressure volume product. Okay, pressure volume product is also called as flow energy. So I can write u1 plus p1 v1. I can write that, or directly I can write h1. Okay, it should be equal. These are the inlet, should be equal to m dot into h2 plus v2 square by 2 plus g into z2 plus your power developed or work done. This is the equation. Now, majority of the times, we place the compressor in a horizontal positions. So, the kinetic energy changes automatically, it reduces, or there is no kinetic energy. And your heat loss, see, the compressor casings are well insulated. Well insulated. See, enthalpy change is different. Heat loss is different. So Q also is neglected, or it is should be 0. That means it's an assumption. Let us assume your heat loss 0 and it is horizontal, Z1 is equal to Z2. So what will happen? This will become m dot into h1 plus v1 square by 2 is equal to m dot into h2 plus v2 square by 2 plus your work done. Okay, so let me call this as some equation number 1. Now, if you closely observe this thing, what is it actually? We know the expression. What is H naught? H naught, we have the stagnation enthalpy. H naught is equal to H plus V square by 2. So what I can write? I can write this as m dot into H naught 1 is equal to m dot into H naught 2 plus work done. Okay, see why this particular thing, to be very precise actually, this is actually specific stagnation enthalpy. Specific stagnation enthalpy. Or I can write your W is equal to m dot into. So this I'm going to bring it to the other side of it because see one particular thing you have to be a bit careful here. One more thing. Now, so if I call this as equation 2, now for a compressor, your W is a work absorbing machine. See, this should be plus or minus. So very precise. This should be plus or minus. Okay, that's what we write. Now minus the W plus W. So minus W means actually this is a work absorbing device. So usually a compressor or a fan, all those things, it comes in that particular direction. And if it is positive, it is a work producing device. So usually that is your turbine. So if I put W is equal to H1 H01 minus H02, it becomes a, see, the same thing. I can write W is equal to m dot into H01 minus H02. This becomes a turbine. Okay. Now here I am trying to increase it. So this I can write it as H02 minus H01. This is for a compressor. Why it is? If you observe here, my enthalpy at the exit is higher than the enthalpy at the inlet. So m dot into H naught, I can write it as capital H. So the total enthalpy. So W naught is equal to H02 minus H01. This is in terms of total enthalpy for that particular compressor. I can call this as equation number 3 or whatever it may be. So I can write this particular thing, H naught or whatever it may be, I can write in terms of total enthalpy, or I can leave it as m dot into H02 minus H01. Now, if you go back to your thermodynamics, your enthalpy is a function of temperature, and also your internal energy is also a function of temperature. Both are functions of temperature. So what we can write, you hope you remember that you might have written like this: H is equal to Cp into T, and U is equal to Cv into T. Go back and little bit brush up on this particular thermodynamic relations, how it is actually, how we got it. So I can write H is equal to Cp into T, where Cp is the specific constant pressure and Cv is the specific constant volume. So I can write this particular. Now, here instead of static temperature, so it's a function of temperature. It can be a function of a static temperature, or it can be a function of stagnation temperature. So I can write this particular equation. I can write, therefore, your W dot, I can write it as m dot into, okay, Cp into T02 minus Cp into T01, or I can write m dot into Cp into, which is constant. This is my equation, what I am getting. So this is the equation for work done, m dot into Cp into T02 minus T01, where T01 and T02 are absolute temperatures. Absolute temperatures. What is T0? So T0 is equal to T plus Cp square by 2Cp. Hope you remember that particular formula. I can use that, and I can write that particular stagnation temperature in terms of static temperatures also. Okay. Now moving further. Now let us look at this particular thing, the HS diagram. See, you have enthalpy. See, if I try to draw a simple horizontal line here, Let's try to draw an horizontal line here. So this will be my H naught 2 dash. This will be my H naught 2. This will be my H naught 1. Okay, I can write the compressor efficiency. The compressor efficiency is nothing but your ideal work done to actual work done. So what it will be? H naught 2 dash minus H naught 1, that is ideal work, divided by H naught 2 minus H naught 1, which is my actual work. Okay, so efficiency of the compressor, I can write efficiency of the compressor. Efficiency of the compressor. What it is actually is equal to H naught 2 dash minus H naught 1 divided by H naught 2 minus H naught 1. Or if I write in terms of temperatures, this will be Cp into T naught 2 dash minus T naught 1 divided by Cp into T naught 2 minus T naught 1. Or I can write Cp will cancel out. This will be T naught 2 dash minus T naught 1 divided by T naught 2 minus T naught 1. So I can call this as equation number, this I can call it as equation number 4. This I can call it as equation number 5. So now maybe few books they give this compressor efficiency as total to total efficiency. Either I can write it as compressor efficiency or I can write it as total efficiency. Both are same. Okay. Now what I will do a little bit of cross multiplication. So I will write in terms of T02 minus T01. So T02 minus T01 is equal to T02 dash minus T01 divided by compressor efficiency. So what I'm going to do, I will try to substitute for T02 minus T01 from equation 5 in equation 4. Okay. Substitute for okay, the temperature change, that is T02 minus T01 from equation 5 in equation 4. Then what will happen to your W? So therefore, your W dot is equal to, okay, I'm writing in terms of this thing. So M dot into Cp, okay, either I can write, either you can write in terms of M dot into Cp, or you can just simply MM also will just see M dot into Cp, or you can take mass flow rate as per kg also, doesn't matter. So everything will drill down to 1 kg. I can write in terms of per kg also, doesn't matter. So it will be simple, Cp into T02 dash minus T01 divided by compressor efficiency. So assuming if M dot is equal to 1 kg per second, if I do that, so this will be simply Cp into T02 dash minus T01 divided by compressor efficiency. Or I can write W dot by Cp is equal to T02 dash minus T01 divided by compressor efficiency. I am calling that as equation number 6. Okay. Now let's go back to your thermodynamic relationships. Come back to this particular. Maybe instead of HS diagram, if I consider the TS diagram. Consider the process 01 to 02 dash. So I can write P2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. That's from the thermodynamics. So instead of static temperature, if I write it in terms of stagnation temperature, this will become T02 dash by T01 is equal to P02 dash by P01 whole to the power of gamma minus 1 by gamma. Okay. For an isentropic compression, for an isentropic compression, for an isentropic compression. So we have, see, this is the expression what I'm going to write. T02 dash by T01 is equal to P02 by P01 whole to the power of gamma minus 1, because we have this relation from the thermodynamics. T2 by T1 is equal to P2 by P1 whole to the power of gamma minus 1 by gamma. This is only for isentropic compression. So here little bit I want in terms of pressure. Actually, I can write P02 by P01 is equal to, so it will become gamma by gamma minus 1. I can write this will become T02 dash by T01 whole to the power of gamma by gamma minus 1. So I'm going to call this as equation number 7. Okay. Now what I'm going to do, so here I'm going to do some kind of an modification or some kind of an addition or subtraction of this thing, so that I can substitute this particular thing over here. That is, I will substitute T02 dash by T01 here. So add and subtract T01 in the numerator. Okay. So that is P02 dash by P01. Okay. P02 dash means it's P02 only. Okay. P02 by P01. So because P02 dash and P02 both are same, is equal to T02 dash minus T01 plus T01 divided by T01 whole to the power of gamma by gamma. So that is add and subtract T01 in the numerator. If I do that, so if I'm going to take only this expression, look at that particular expression, and I'm going to look at this expression. So what will happen? I can write W by Cp into compressor efficiency. I can write substitute for that particular thing. Substitute for T02 dash minus T01 from equation 6 to get P02 by P01 is equal to W by Cp into your compressor efficiency plus T01 divided by T01 whole to the power of gamma by gamma minus 1. Okay. Further, I can simplify it as the same expression. I can write it as P02 by P01 is equal to, okay, W by Cp into compressor efficiency divided by T01 plus 1 whole to the power of gamma by gamma minus 1. Either you can write like this, or some of the books they write in this fashion. P02 by P01 is equal to 1 plus W by Cp into compressor efficiency by T01 whole to the power of gamma by gamma minus 1. Gamma by gamma minus 1. So this is your equation number 8 actually. Okay. So this is your expression for pressure ratio. Either you can write in terms of C. Now, there are a couple of textbooks actually where they try to write this the same expression in terms of Euler equation. So this is your general expression. And maybe because we have to discuss with respect to the slip factor, all those things and all, which comes into picture here. Slip factor and all, which comes into picture. So to do this actually, factors affecting this stage pressure ratio. What are the factors? Then we look into that particular thing. So today we'll try to stop at this particular thing where we have got the expression for pressure ratio. This is expression for the pressure ratio. Now